Thank you. So thank you all for being here. I think you'll all be fine, so don't panic beforehand. So like Susan mentioned, I'm Marcel Kornegoor. I'm a director at AT Computing, where I torture my team with word jokes. And besides that, I'm also a part-time nerd. So during night, I fiddle around with open source technology to get things working. But that's not what I'm going to talk about today. Why am I here? During my daily work, I talk a lot to companies and customers that have struggles with learning. So they have a lack of knowledge, or they want to investigate how they can make people go from the old legacy world towards a cloud-native world. And that got me a lot of insights and lots of observations about what's going on. So today, I want to share some of these observations with you and share my thoughts on them a bit. So what I found is that in general, and this is not bound to the Netherlands where I'm from, but more a general over Europe or maybe global, that companies struggle with technical debt. So they have this old system that should have been updated, or that should have been patched and migrated already, but it's not happening. And it can be that the system itself is not outdated, so it's not true legacy, but they struggle with new features versus technical debt. And I've heard it around the conference here as well, that it's a big issue. Also, separately, they struggle with legacy systems, where they say, well, most of our money is still made by systems that are really old, and we cannot leave them because then we have no money to pay for new systems. So it's a bit of like stuck between a rock and a hard place. And that's quite interesting. Like, why have all the companies the same struggle in this area as well? So another observation is that if there is a merger or an acquisition and the company is in the same branch, it's very likely to have applications be merged into one and to have some efficiency gain. But companies struggle with that as well, because every company thinks it's really special and really different. So applications tend to pile up instead of getting rationalized. And that's also like a general observation of a lot of companies that struggle with it. And that has as a consequence that a lot of companies struggle to innovate. So they say, well, we want to pick up speed, we want to have our best people do innovative things, but they really struggle to get it done. And that's not without the governance that they experience. So a lot of people say, well, we want to speed up, but this manager needs to approve, or the company is really slow. And that's also like a general observation that a lot of companies say, our people are ready, our people want to do it, but the organization doesn't pick up. So I think this all relates to the same underlying principle, and that's that companies, and maybe us here at DevOps Days, struggle with complexity. So IT systems are complex, and to change them and to make them more modern is complex, and that's really a big puzzle. So the baseline is that if you look at what happens there, is that we really, as humans, have a hard time making things easy and keeping things easy. So creating simple systems and maintaining simple systems. And we all probably know the KISS principle, keep it simple, stupid, or something like that. And we all know it, but that's not what we actually do, is my observation. So this made me wonder why. So I've seen this, I've thought about it, and I thought, well, is it just this simple? Is it just that we lack some form of motivation, or are we not intelligent enough to do so? What's the reason that all companies struggle with these kind of challenges? And that made me think, like, what is the human being as a species? And well, if you look into the psychological directories, we are quite peculiar. So we have this tendency to create organizations that have a big appetite of managing risk. So we have separate departments for it. Managers are hired to manage risk. Also in our daily work, we see a lot of risk and we want to contain it to make sure that things are safe. But the problem is we are really, really, truly bad at it. So we are basically in the car driving full speed and say, well, it's going great because our speedometer is pointing us in the right direction, everything is okay, but nobody mentions that we're hitting a wall if we do not brake. And we are really, on different levels, bad at this kind of risk management. So that's interesting, but how bad are we actually? This is actually some numbers from a Dutch bank. They did some research on how bad the cybersecurity situation is actually. And they said, well, nowadays a company has a 1 in 5 chance that there will be some form of cybercrime. So ransomware or some other hacking going on. That's quite a big risk for a company, compared to the hazard that a company might catch fire. That's 1 in 8,000. So that's really like a different scale. And how bad are we at risk management? You would say, well, cybersecurity should be the top priority when we want to maintain risk. But that's not how we do it in practice. Because nowadays you're not allowed to fart in the office anymore because the gas will increase the fire hazard. There's a rule for that. But on the other hand, root passwords may be spread around multiple engineers for the same systems, mission critical, and that's fine. So that's really strange if you look at the statistics from the actual risk, as long as it's, of course, neatly documented where those passwords are. That's also a rule. But this got me thinking further, like, why are we so bad at this? So why is this actually what we're doing, where we say that we are risk aware and we are proactive, etc.? We are not. So things first need to go terribly wrong before something changes, actually. And yesterday in the Ignite, there was also an example about airplane operators. There first need to be an airplane crash before there will be a change in the rules so that it will prevent it the next time. And that's just the way we are wired, probably, or how it works. And that's quite intriguing. Like, why is it that way? So why are we so reactive when we have the bias or the opinion that we are quite proactive or want to be proactive? So again, why? Why is this? Why are we making things so hard on ourselves where we know that there is an easier way? And that's where I start thinking, why is it so easy and why are we so good at making a mess? And why is it so hard to keep things clean and tidy? Is it because we have business that makes stupid decisions? Is it because the sales department, need I say more? Is it because, in general, C-level people are morons? Or does it have to do with politics? Might be. I think not. I think there's something else that's all together making us do the things we do. And it does not rule out all the other factors. They might have some influence on things, but there's a more fundamental principle going on that makes things the way they are. And that's the second law of thermodynamics. So, what is thermodynamics? It is some science topic, and I need to put up a disclaimer here. I'm just an IT guy. I have no PhD in physics. I'm not a scientist. I have no degree in whatever mathematician stuff. So it might be that there will be some calculation errors, but please give me some slack. So thermodynamics is a field of study that discovers the relations between heat, work, temperature, and energy. So that's like the 4 ingredients this field of science discovers or experiments with. And this comes from a machine we probably know, the steam engine. And back in the days, like the 18th century, there was an invention, the steam engine, but it wasn't really efficient. So a scientist, a Frenchman named Nicolas Sadi-Carnot, spent a lot of time investigating how can I make this steam engine more efficient. And the reason he wanted to do it, because he wanted to have France to be a leader in this new technology era. So he thought if we have the most efficient steam machine, the most efficient steam engine, we can be ahead of the competition. So basically, the last few decades, nothing has changed. We now have this on machine learning models. It's the same principle. We want to be ahead of the pack. He did it with the steam engine. And when he was investigating it, there came more of awareness that a perfect engine could be possible on paper. But it was really hard to build it in real life. So a steam engine had really a lot of issues, a lot of inefficiencies, and that was where thermodynamics was born, to see how does it work actually. So why would thermodynamics be interesting for us IT pros? Well, a reason, and probably an interesting reason, is that there are a couple of laws that start counting at 0, which is a good thing. And that 0th law is basically stating that if you have 3 separate systems that are in the same, 3 separate subsystems that are part of a greater system, if 2 systems of those are of the same temperature or in equilibrium with each other, the 3rd system must be as well. That's like the fundamental reasoning of thermodynamics. The second has to do with the conservation of energy. And this is what probably a lot of you will know. It's part of thermodynamics where you can say, well, if you have this system doing something, so there's energy put in, there should be an equal amount of energy put out, because energy doesn't disappear. It can only change a form, but it should be consistent before and after. So that's what the first law describes. And you can see here the formula, that's the first formula, that the total energy of the system on the left will be conducted when you look at the work that it provides and the heat that's put in. So that says something about the efficiency and about the energy of the system. So the second law is all about looking at how does a system behave. So it's not about the efficiency of the system, but the nature of the system. And this means that the second law actually defines that if you have a system, a closed system, it will eventually tend toward an equilibrium. So it will reach some stable point, and that's the end of what the system will do. And this law also makes clear that it's not possible to have some form of perpetuum mobile. So you can not have an internal running engine, because there is no such thing, because there's always a form of loss of work that you experience. So there's the third and final law. So it's actually 3 laws and a 0th one, so that's 4 in total. That says that if you reach absolute 0, there will be reached a constant, because there's no movement, so there is no energy transfers, etc. So that's like the starting point of nothing happening. So let's zoom in on that second law, because that's what's the important one for IT systems as well. And this is a formula that describes what's called the concept of entropy. And entropy has something to do with how useful is the energy of a given system, and how useful can it be used to get some work done. And that can be transferred, or it can be increased or decreased. And as you can see in this formula, so the total entropy of a system is reached by counting all the separate parts that the system is built of. So let's assume that you have some cold system and a hot system. Then the entropy of the cold system plus the entropy of the hot system makes the entropy of the total system. And this implies that the entropy of 2 combined systems can only increase or stay the same, but it can never decrease. So if you combine 2 things, it will probably increase and never decrease. So how does this work in real life? And that's why I have this water with me. Because I here have, first, before I touch the bottle, I have some safety procedures for my corporate risk manager. So I need to make sure that I do not get in touch with a concentrated liquid that's harmful to the human body. And when I got this remark, I was like, why? It's just some syrup. But if you know how much sugar is in there, it's really harmful for the human body, so I get it. So, let's see. This is low entropy stuff. So, a lot of energy is contained here, right, in this bottle. And this is my second system. So you can see this as the hot and the cold system, system 1 and system 2. And now I'm going to pour some low entropy stuff into the other system. We probably all know what will happen. It will mix. All right. So, now, for sake of the experiment, I will make it a closed system and put on the lid again. So I can remove my safety goggles and my gloves. All right, so what eventually happens is that the orange stuff will spread out evenly over the water. And that's quite interesting, because why does this happen? Anybody, any clue? Why does it happen? Because it can. That's interesting. Yep. Diffusion, not so much. It's really because it can. And it's basically the same principle that's fundamental for your coffee cooling off and not heating up. And the fun thing is that if you look at why this is not because it's, from a science perspective, impossible. So the laws of physics do not exclude the possibility for something to heat up spontaneously from colder things around it. It's just so improbable that it will never happen. So the reason that the syrup is spreading out over the whole can of water is just because that's the probable thing to happen. It's really improbable that it will all clump up like in this corner. It's not impossible, but it's so improbable that it will not happen. And that's quite interesting. So it's really a fundamental physics thing. This is really a cornerstone of everything around us, basically. So, yeah, I explained a bit why. So why is this? It has to do with probability. And if we look at another real-world example, we have seen a steam locomotive that can also have low entropy. So in this case, there is a low entropy locomotive. It's nicely on the rails, and this is useful because you can transport people from one place to another, and it has a lot of use of the energy you put in it. So you're creating a fire, you're making steam, and you can do something with it and transport people from A to B. So that's great. Low entropy is useful. But if you have the same object in a situation where there's a higher entropy, it might look like this. So it's the same train, but it's higher entropy, and it's less usable. It's less usable because with that train, it's a bit harder to transport people from A to B. It's not in the place where it needs to be. And this concept is universal. So my favorite DevOps t-shirt, there's only one possibility that it's neatly folded in the drawer besides my other favorite t-shirts. But there are a lot of possibilities that it's just like laying around somewhere and I need to pick it up. So it's easier to throw it on the floor than it is to neatly put it in a drawer. And this is everywhere, and this is just nature. It's just probability. So if you look at this from an IT perspective, we know some situations where we create a lot of entropy without doing actual useful work. So in this case, if you have an infinite loop in software, it's high entropy, but it's not doing like real work that can put any value into your application. So it uses energy, but not in an efficient way. And it produces a lot of heat. And heat is not the same as warmth, but it's energy that's so diffused that it's not usable anymore. So the energy is still there because of the conservation of energy, but it's in a less usable form, so you cannot make any use of it. It's dissipated and it's gone forever, probably. Also, this is also a form of entropy increase. Because now you have two systems with the same data. So this is also free security advice. The probability of your private data being not only in one place, but in many places, is really probable. It's nearly 100% chance it will eventually happen. So if you have budget issues, please, this is science talking, not me. It will happen. So this means that over time, software will become complex automatically. If you do nothing on a system, it will break. I have never seen my car being fixed spontaneously. It only breaks spontaneously. Also, IT architectures and IT landscapes will get complex over time if you do nothing. So the complexity is like free lunch. It will happen spontaneously. So the question is, what can we do about it? So can this entropy be reduced? So if we look at the train that was like riding through the station, it can be put back on the rails, right? It can be fixed. So yes, entropy can be reduced. So that's mainly because the IT landscape is not a closed system. This system is closed, so I can do nothing about it. If the syrup is spread evenly, then the system is at its final state. The entropy has maximized within the system, and there's nothing you can do to reduce it. But if you have an open system, so let's assume I take the lid off, I could build a filter and filter out the syrup again and have it put back in the flask. That is possible. So also within IT, this is a possibility. But thermodynamics state that if you want to achieve such a thing, there is a loss of energy. So that means that if you want to reduce entropy, you should put more effort in than what was required to create the system in the first place. So that means that if you have taken one sprint to create a feature, it will take more than one sprint to take it out again, because it's not a perpetual mobile system. It's not free energy. You need to put work in, energy in, to reduce it. So we really need unfeature sprints. We really need to actively try to reduce the entropy of our RT landscape. That's the only way out of it, because otherwise it will only deteriorate over time. You need to actively put effort into making this happen. So, to all of you, keep fighting. It's necessary to make sure that you eventually get your system manageable. And also, keep infusing new energy, because the only way to reduce entropy is to make sure that you put more energy into it. So if you want to have the train back on the track, there should be external energy put into the system to make sure that it will happen. And you all here are a source of low entropy. You all have the possibility to interfere and to reduce that entropy. And this works also on a global scale, and also with machines in your home, probably. Because if you look at the refrigerator, that's doing the same thing. It's making the inside of the refrigerator cooler than the surroundings. And it does not so by magic, but because somewhere else there is entropy increased. So there might be a windmill that needs to be built to generate the energy that's necessary to power your fridge. But the transfer of the energy has some heat, so there's dissipating energy from it. And all that dissipation, all that increase of entropy makes it possible to reduce the entropy of this small system. And that's the whole mechanism. That's everywhere. That's also with IT systems, with architectures, etc. And it's also with the sun. That is our global planetary source of low entropy. So the sun offers us clean, low entropy energy, and all systems on Earth, the plants, the animals eating the plants, etc., it's all a chain of increasing entropy for different types of work. This is the lowest source of entropy we have in our nearest environment. Lower than the sun is really hard for us at Earth. So this means that all your blood, sweat, and tears you put into unfeaturing some application will dissipate into the universe. It's part of what you have put into it to reduce the entropy, but it will not get actually transferred to work. But sadly, the probability of this happening is really low. It will not happen. So that's the reality. It can be done, but if you now go to your manager or the director or your product owner, you will say, well, we will now introduce the unfeature sprint, and that will take half our time. I think there might be some risk management discussions. Or AI will solve this. So after a lot of thought, a lot of observations, and diving deep into what makes this happen, I think that we can say, well, the probability of us as humans making simpler systems is just really improbable, and the chance of it happening is nearly zero. And that means, as Harold and Kumar also discovered, we have to deal with it. It just unfolds as it should. It's just the way it is, and we better embrace it instead of trying to fight it. Thank you.